Happy Monday after the exam. How was the exam? Good? I like to hear that. How many of you felt like it was what you expected? A few. That means the rest didn't think what was what they expected, or they didn't raise their hand. So, hard, easy? Hard, okay. What was hard? The questions? The last page, the matching was hard? Okay. Yeah. Other thoughts? I can't make any sense out of what anything anybody's saying. Yes?
I studied like I did last term.
Uh-huh. Yes.
I felt that there's a different level of study.
Yeah, a different level of expectation between last term and this term. And that happens even when I teach both terms. BB 450 tends to focus more on problem type things, and BB 451 tends to be more metabolic, which tends to lend itself more to nomenclature and pathways and so forth. But yeah, I appreciate that. Yeah, hand back here.
I was going to say the multiple choice where you don't specify how many are going to be correct
Yeah.
or how many are going to be false. That's pretty fun.
So people always call those the multiple choice. They're only the true false is all they are. So if you circle if it's true, you don't circle if it's false. And you get a point every time you get one right. So it's not like you have to get them all right to get points. Yeah. I'm not quite sure why people see those as multiple choice.
I like that explanation better than what you have written on the test.
Yeah. That's all it is. It's true false. You circle if it's true, you don't circle if it's false. If I put true false out in front of there, you wouldn't think of it as a multiple choice exam, would you? And everybody goes, oh my God, I didn't know that was a true false. Right? That's why I give the exam in advance and ask people to read the instructions. Yeah. Other thoughts, questions, comments? Okay, well, thank you. The exams are not yet graded. Once they are graded, I will let you know, and we usually have specific times to pick them up, and I will post those as soon as I have them from the TAs. The TAs are working pretty hard on them. I'm not anticipating a very long cycle of grading, but they have their own schedules as well, so they're in the process of doing that. I don't post a key until we put the exams back, but once I put the exams out and available, I will post a key outside of my office that you can check your answers and so forth. Okay? All right. Well, last time I got started talking about the movement of cholesterol in the body, and this is a fascinating topic, and as you can see, it's a bit complicated, but I like this figure a lot because I think it really shows the three processes that are involved in this overall thing. So the process we've talked about so far is outlined above in green, and that's the dietary input of cholesterol and lipids in the body. I'm going to focus mostly on cholesterol today. Cholesterol is a fascinating topic because there's so much about it that we don't know. Believe it or not, there have been 7 Nobel Prizes awarded for cholesterol. And we still have a lot of things about cholesterol that we don't understand. So it's a topic that generates probably as many questions as I get from anything that I talk about, because cholesterol is something that people can relate to. They've had relatives, for example, who've had issues with atherosclerosis and other problems associated with cholesterol. Well, dietary cholesterol, as I said, comes in and gets packaged up into chylomicrons. Those chylomicrons go out to the capillaries, get stuck, and they get some of the contents get digested away. The contents that get digested away are not the cholesterol. That's the fat primarily that gets digested by lipases. And those fatty acids come out. They can be gobbled up by the free fatty acids, FFAs there. They can be gobbled up by adipocytes to make additional fat. They can also be gobbled up by cells and used as energy sources, and we'll talk about that later on today. The remnants get smaller as a result of that digestion. I like to think of the part in the middle of the chylomicrons being like the center of an Oreo cookie. You start eating away the center of the Oreo cookie gets smaller, and as a result, it now fits through the capillaries more easily. The chylomicrons make their way back to the liver, which absorbs them. It takes them in. It's obviously important for the liver to have the capacity to handle the lipids, to handle the cholesterol, to handle the fat-soluble vitamins that are in those lipoprotein complexes. At that point, the liver really has a decision to make. And the decision that the liver has to make is, well, what is the body needing? So I'm going to tell you, first of all, what happens when everything's working great. Okay? So let's say the liver decides the body needs some cholesterol and some lipids. Okay? Now I'm going to tell you later how the liver knows that, but first we'll just say the liver has decided that the body is needing some cholesterol. So what does the liver do? Well, the liver at that point takes and it packages up cholesterol and some lipids, including fats and so forth, into other lipoprotein complexes. These other lipoprotein complexes are known as VLDLs. You can see it right there in blue. Very low density lipoprotein complexes. These are pretty big and fluffy. They're not quite as big and fluffy as the chylomicrons were, but they're also pretty good sized. These also are not involved in atherosclerosis. They go out into the bloodstream, and like the chylomicrons, the contents of these start getting digested away. And as the contents start getting digested away, the complexes become smaller and smaller. So the VLDLs become the IDLs, intermediate density lipoprotein complexes. They're smaller and they're more dense. Okay? The IDLs get broken down into smaller complexes known as the LDLs, the low density lipoprotein complexes. And it's actually these guys that are implicated in atherosclerosis. I'm going to tell you why in just a minute. The LDLs have the highest concentration of cholesterol of the complexes I've told you about so far. Okay? Because the fat has been digested away, but the cholesterol has not been touched. So as a consequence, as a percentage of weight, the percentage of cholesterol has been going up, up, up as we've gone from VLDL to IDL down to LDL. Cholesterol only makes it into cells as a result of a process known as receptor-mediated endocytosis. That's a long phrase that basically means that cells grab a hold of it and absorb it. And I'm going to show you that in just a minute. Okay? Receptor-mediated endocytosis. That means that the entire LDL, or at least what's left of the LDL, is taken up by cells and internalized. Well, not all of the LDLs get internalized. How much gets internalized? Well, it depends on the needs of the cells of the body. If the cells are needing lipid and needing cholesterol, then more of those LDLs get taken up. And if the cells are pretty fat and happy with lipids and with cholesterol, okay, then they won't grab and take them out of the bloodstream. And in fact, what will happen is that those LDLs will make their way back to the liver. So that's what we see here. We've gone VLDL to IDL to LDL. The LDLs can feed their cells. The LDLs can release free fatty acids that can go off to be fat in fat cells. And if they get all the way down here, they can go right back up to the liver. Further, as we'll see later, they can go and become something called HDLs. Okay? Now, we're going to focus on the LDLs going back to the liver, going back up that blue route there. Now, this turns out to be a critical route because the number of LDLs that make it back to the liver, okay, tell the liver how much the body is needing cholesterol and fat. The more that make it back, the less the liver says that the body needs. Right? Because from what I've just told you, if the body's needing a lot, it's going to start grabbing all of them. If the body doesn't need them, it's going to let them float along in the bloodstream. Therefore, the liver is sensing how many LDLs make it back compared to how many LDLs I put out. That means that the liver has a special kind of a receptor called an LDL receptor. Cells out here also have LDL receptors, but the liver one is different. Okay? The liver LDL receptor is different. What does the liver LDL receptor do when it binds to an LDL? It internalizes it, just like the cell receptor does. But the liver one is different. Now, the difference of the liver one is critical because mutations in the liver LDL receptor have drastic consequences. Let's imagine that you mutate the LDL receptor of the liver such that it can't bind to an LDL. What do you suppose the liver would do in response? It would start putting out a ton of LDL because it would never get a signal that these guys are coming back, because that's what the LDL receptor is telling them. Okay? There's a genetic disease known as hypercholesterolemia. I'll put it in the highlights. Hypercholesterolemia. Okay? I had a student in this class who told me that her kid had hypercholesterolemia. And I said, no way. Hypercholesterolemia kills people by the time they're 10 years old because their LDL levels are enormous. I'll give you an idea. Okay? LDLs are what your doctor measures in your bloodstream to determine if you have high cholesterol or not. A reading of about 200 usually is an indicator to the doctor that we've got to start watching your cholesterol. I'll talk about why in a minute. We've got to start monitoring your cholesterol. Okay? People with hypercholesterolemia, including this woman's son, had LDL levels of over 700. They typically, before the advent of drugs, which is what her son got in on, fortunately, before the advent of drugs like the statins that I talked about to reduce the production of cholesterol in the body, okay, those people who had hypercholesterolemia typically did not live past about age 8 or 9 because they died of heart attacks. Her son, as a result of the fact that he was born after statins had been developed, they were developed in about the 90s, lived a normal life, or is living a normal life, because they were able to treat him and get his cholesterol levels down to about 200 or so. Okay? Pretty remarkable thing. So, deficiency of LDL receptors will cause high levels of LDL in the body. Well, why are LDLs problematic? Why are LDLs problematic? LDLs are problematic because they are the form of lipoprotein complexes that are the most likely to get oxidized by reactive oxygen species. They're the most likely form of the lipoprotein complexes to get oxidized by reactive oxygen species. Specifically, what happens to them is that these guys carrying fatty acids in the fat that they have in them, and yes, they still do have fat in them, get oxidized when a reactive oxygen species binds to them. Well, how do you get high levels of reactive oxygen species in your blood? Remember, we're talking about blood now, outside of the cell, not inside of cells like in mitochondria that I've talked about. How do we get high levels of reactive oxygen species outside of cells? The easiest way to do it is to smoke. Smoking increases your levels of reactive oxygen species floating around in your bloodstream. Well, smoking and heart attacks go together. Everybody knows that. Okay, heart attacks and strokes and all these things go together. Well, what happens when an LDL gets... Question? Or somebody coughing? Okay. What happens when an LDL gets oxidized? What happens when it gets oxidized is the body sees it as a foreign body. Macrophages of the immune system bind to it. And if that happens on an artery where they can get attached, then all of a sudden everything gloms onto this attachment site on the artery. You form what's called a foam cell because this thing is just full, it's foamy looking, because these LDLs are full of lipid. Mix lipid and water, what do you see? You see foam, okay? Those foam cells, they're not cells, they're called foam cells, but those foam cells, okay, can, in fact, give rise to a plaque, a solid form that causes a heart attack or causes a stroke. So the reason your doctor is interested in LDLs is because they're the form that correlate with incidence of atherosclerosis. Okay, well, there are things that will save your butt. One of the things that will save your butt are HDLs, high-density lipoproteins. And HDLs are assembled by your body, okay, to scavenge problems that are out there. Scavenge problems, maybe broken LDLs, maybe free-floating cholesterol, maybe a variety of things that are out there. They're scavengers. And these scavengers will grab these damaged things and haul them back to the liver, where the liver says, okay, let's start over and do it right. HDL is what your doctor is likely to refer to as good cholesterol, because high levels of HDLs correlate with lower levels of atherosclerosis. Okay? They've got cholesterol in them too, but they're headed right back to the liver to deposit it back in the liver. Okay? So HDLs correlate positively with lower levels of atherosclerosis. How do you increase your HDLs? Well, 1, lose weight. 2, exercise. Exercise is very beneficial for production of HDLs. Those two things right there, there's your New Year's resolutions for you, will help lengthen and make the quality of your life much better. Okay, questions about that? Yeah, question? Yes. That's a good question. Given that the plaques are part of an immune response, would somebody with a compromised immune system have a lower level of atherosclerosis? To be honest, I don't know. I don't know. It would be a little hard to say because compromised immune systems have other problems associated with them, and compromised immune systems may also lead to higher incidences of cancer. Which could also be problematic. So it might be, but it would probably be hard to sort out the various variables I'm thinking. But it's a very good question. Okay. Well, let me show you a couple things relevant to this. I promised I would show you the endocytosis. So let's start with that first. I told you that cholesterol is taken up when the entire LDL is absorbed by a cell. So a target cell that is needing some fat, cholesterol, etc., will take up an LDL. It's complicated, though, about whether it needs it, because remember that cholesterol can be synthesized by cells, okay? It can be stored, and this is the third way, it can be taken up from the bloodstream, ultimately as a function of coming from the diet. So those three things there are variables that happen, but we can see this process where an LDL, which and I was partly responsible for this figure, so I'll claim blame for it. I've drawn as a triangle there. You don't really see a triangle structure on here, but the important thing is that there are receptors on the surface that recognize molecules on the LDL, grab a hold of it, and internalize it. And so we can actually see that internalization process happening here. Everything sort of gets unpackaged, and the components that were there, the LDL receptors, are released back to the cell surface. There's a protein called Clathrin that plays a very important role in that process, and the role of Clathrin is shown here. No, I'm not going to ask you to recreate this image in any way, so don't sweat that. I'm just showing you this, to show you that Clathrin is a cellular protein that helps the pinching off of that little vesicle to internalize the LDL. So if you know that much about Clathrin, you know as much as you need to know. So Clathrin is a cellular protein that helps the pinching off process during the phenomenon of receptor-mediated endocytosis. Okay. There's a foam cell aggregate, and I lied a little bit. I said there aren't cells. The macrophages, of course, are cells that are involved in this process, but the foam cell aggregate is larger than just the macrophages themselves. And here's what, it's kind of grotesque, what an atherosclerotic plaque actually looks like. And you can see here that something has gotten attached at a critical place in an artery, and this whole process has sort of snowballed. Okay. So that's what I want to say about cholesterol and the movement in the body. I'll talk later a little bit more about cholesterol and metabolism and so forth. Let me first of all talk about fatty acid metabolism. So, we've been talking about or dancing around lipids and so forth. We talked about glycerophospholipid metabolism and also sphingolipid metabolism, but we haven't talked about fatty acid metabolism, so I want to do that. Remember that fatty acids are breakdown products from fats, and you saw in the figures just a few minutes ago how fatty acids can be released from the various lipoprotein complexes and taken up by cells. So the taking up of fatty acids by cells is what we're going to start following here. So I want to imagine, first of all, that we've got a cell that has released some lipases to some of the lipoprotein complexes around it, and some free fatty acids now it has internalized. Okay? There's another way that the cell could have gotten those free fatty acids, and that would have been by serum albumin, of course, which is a transport protein in the blood that carries those free fatty acids. It could have gotten them from that as well. How the cell got the free fatty acid, we're not going to worry about for the moment. We're only going to be concerned about the actual metabolism that's going on. So I'm going to start this discussion here with the second slide, which is the activation. The activation of the metabolic process for oxidizing fatty acids starts with the internalization, and then there's a kind of a curious path that the fatty acid goes through inside of the cell. So I'm going to take you through that path to understand that. Here's a long chain, here's a fatty acid that has come into the cell, and fatty acids in the cell are just like fatty acids outside of the cell. They're problematic if they are free. The reason that they're problematic, as I mentioned last time, is the fact that they can act as detergents and can denature things. So the cell avoids problems associated with them being detergents by attaching a handle onto the end of the fatty acid. That handle you already have heard about before. It's coenzyme A. And we refer to this structure that's been created by the attachment of the coenzyme A as a fatty acyl-CoA. Okay, not acetyl-CoA, all right, or not acetyl-CoA, but rather fatty acyl-CoA. Acyl referring to the long chain that's out there. So we've got a fatty acyl-CoA. Putting that CoA on there takes energy. This energy is provided by ATP, and it's the equivalent of 2 ATPs that it takes to put on there, because when you go from ATP to AMP, that means 2 more phosphorylations are necessary to put that, those other 2 phosphates back on there to regenerate ATP. So this is an significant energy requiring process. But it's important because cells want to have that handle on there so that they don't have this problem that I've described to you of detergents. Well, then something curious happens. This reaction occurs in the cytoplasm. Okay? Once the fatty acid has gotten into the cell, this reaction occurs. Getting the fatty acid into the mitochondrion, however, is critical because the oxidation of fatty acids occurs in the mitochondrion. Well, there's a transport system called a translocase that moves the fatty acid into the mitochondrion, but something curious has to happen first. The something curious that has to happen first is that the CoA that the cell just put a bunch of energy into attaching to it has to be removed. Now, we're looking here in the outer portion of the inner mitochondrion. That is the intermembrane space between the outer membrane and the inner membrane. In that intermembrane space, there's an enzyme called carnitine acyl transferase 1. And yes, that's an important enzyme. Okay? Carnitine acyl transferase 1. It catalyzes the swap of coenzyme A for carnitine. So instead of having an acyl-CoA that we started with, we end up with an acyl carnitine. Carnitine is just a molecule like CoA. In fact, it actually looks quite a bit like CoA. Okay? So carnitine is attached to this structure. All right? Then there's a transport protein, a translocase, that transports the acyl carnitine in as it transports carnitine out. So it's an antiport. We're not going to follow the carnitine. We're going to follow the acyl carnitine because inside of the mitochondrial matrix, the acyl carnitine, the carnitine is removed and replaced by a coenzyme A. Look at that. We recreate the CoA. Is this odd? Yes, it's odd. But the end product, acyl-CoA, is exactly what we started with. Why does the cell do this? Well, because the translocase will not move a CoA across. It's actually got to be replaced by a carnitine. This enzyme here is called carnitine acyltransferase 2, and it's essentially identical to carnitine acyltransferase 1, the difference being it's in the mitochondrion instead of being in the intramembrane space. It's just simply catalyzing the reverse reaction that you saw up here at the top. Okay, well now we have what? We have acyl-CoA in the mitochondrial matrix, and we're ready for some oxidation. Well, fatty acid oxidation turns out to be a relatively simple metabolic pathway. Okay? If we look at the process overall, I'm going to focus you on this slide, which shows you the place where all of the relevant reactions occur. All of the relevant reactions of fatty acid oxidation involve carbons 2 and 3 if we number the carboxyl group as number 1. All of the reactions occur between carbons 2 and 3. When I talked about citric acid cycle a couple of weeks ago, I pointed out to you that parts of the citric acid cycle mimic chemically the reactions of fatty acid oxidation. Specifically, when we started with succinate and we oxidized succinate to make fumarate, we saw a reaction occurring between carbons 2 and 3. That reaction involved the removal of 2 protons and 2 electrons to create a trans double bond. That's what fumarate has. And that's exactly what happens in fatty acid oxidation, as I will show you. Okay? This is an abbreviated form here. In fatty acid oxidation, because all of the reactions are occurring between carbons 2 and 3, 2 carbon pieces of acetyl-CoA are split off in every cycle. Every cycle of fatty acid oxidation has 4 reactions. 4 reactions, and the 4 reactions are identical to the ones that happen in the citric acid cycle. Let's take a look at that. Here's the first reaction. Here's our acyl-CoA. Here's an enzyme called acyl-CoA dehydrogenase. I'm not going to make you memorize all the enzymes, but this is one you're definitely going to want to know. Acyl-CoA dehydrogenase. I'll tell you why in a second. Acyl-CoA dehydrogenase catalyzes a reaction between carbons 2 and 3, and they're labeled alpha-beta up here, by the way. This process is also called beta oxidation. Oxidation of fatty acids, also called beta oxidation. We see removal of protons and electrons from here to create a trans double bonded intermediate with a name that we don't really care about. We do care about the enzyme name, though. Now, this is an exact parallel to the succinate to fumarate reaction. The succinate to fumarate reaction, we pull protons and electrons between carbons 2 and 3. We make a trans double bonded intermediate known as fumarate. And then we go on with the rest of the citric acid cycle. Okay? Why do I want you to know the name of this enzyme? I want you to know the name of this enzyme because this enzyme appears to be important in sudden infant death syndrome. Okay? There are 3 forms of this enzyme. A form that works on long-chain fatty acids, meaning longer than about 22 or so in size. Okay? Or actually longer than about 18 in size. I should amend that. Okay? Longer than about 18 in size. One that works on medium-chain fatty acids that works on things up to about 12 to 14 in size. And one that works on short-chain fatty acids, smaller than 12 to 14. Okay? The long-chain one is found in the endoplasmic reticulum. It's found, I'm sorry, I said endoplasmic. It's not found in the endoplasmic reticulum. It's found in peroxisomes. I apologize. It's found in peroxisomes, cellular structures involved in oxidation. Okay? The other 2 are found in the mitochondrion. It's the medium one that works on the medium chain fatty acids that appears to be deficient in some, not all, some infants that die of sudden infant death syndrome. And the thinking is that these infants are having trouble digesting medium chain fatty acids. Okay? There's a correlation. It's not a cause and effect. But there is a relation between the levels of the medium chain length acyl-CoA dehydrogenase and sudden infant death syndrome. Okay. The second reaction in the oxidation of fatty acids is shown here. And this is a hydration reaction. You remember from your organic chemistry that if you have a double bond and you add water across it, the hydrogen will go to one side and the hydroxyl will go to the other side. This reaction is exactly the one you saw in in citric acid cycle when fumarate went to malate. And you'll remember that at the time I told you that the cell made malate in the L configuration. This guy here is in the L configuration. It's exactly the same reaction. The reaction in the citric acid cycle is catalyzed by fumarase. The reaction here is catalyzed by this enzyme whose name I don't care if you know or not. Nor do I care if you know the name of it. But I do care that you know that you've made an intermediate with a hydroxyl at position 3 in the L configuration. Now I do think you don't have to know the names of the enzymes here. The first enzyme, yes. The other two enzymes I'll talk about in the middle you don't need to know. The names of the intermediates you don't need to know. But you should be able to take the basic structures and chemistry and tell me what's going on. Everything's happening between carbons 2 and 3. The first step involves removal of protons and electrons to form a trans intermediate. Second step involves addition of water to put that hydroxyl on position 3 in the L configuration. Okay? And now we move to reaction number 3. Reaction number 3 is an oxidation. By the way, let me just point out something to you here. Okay? This is a hydration adding water. If I had a dehydration, it would be removal of water, right? A hydrogenation is not a hydration. Hydrogenation means adding hydrogen. Hydration means adding water. Dehydrogenation, okay, which you see here, is the removal of hydrogens, whereas dehydration is the removal of water. All right, we're ready for the third reaction. Remember that the intermediate we made in the second reaction was a molecule that had a hydroxyl at position number 3. And in the third reaction, we're going to oxidize that hydroxyl to a ketone. Again, we see everything is happening right here, now on position 3. Okay? And so with this oxidation, we have something that is a keto acid. Okay? That's the keto part, the acid part being out here. Okay? And this guy, again, I'm not too concerned about the name of the enzyme, but because it's an oxidation, we have to have something to do with those electrons, and those electrons get donated to NAD to make NADH. The very first reaction that I showed you, the acyl-CoA dehydrogenase, used FAD and made FADH2, just like succinate dehydrogenase did in the citric acid cycle. This reaction is equivalent to the malate dehydrogenase reaction, in which the hydroxyl group on malate is oxidized to a ketone to make oxaloacetate. So if you learned those reactions for the citric acid cycle, you automatically know them for this cycle. Okay? Again, name of the enzyme not critical here. Okay, well, I said there are 4 reactions. The 4th reaction is coming up, and in the 4th reaction, we split off an acetyl-CoA, okay? And this is a reaction that's catalyzed by an enzyme known as thiolase. Where have you seen thiolase before? Ketone body metabolism. In ketone body metabolism, what does it do? It takes 2 acetyl-CoAs and it joins them together to make an acetoacetyl-CoA, right? This is simply the reverse of that reaction. In this case, we've got a longer thing hanging off of it, okay? But if I were to have this be a 2-carbon piece and this be a 2-carbon piece, it's just the reversal of the ketone body reaction. So thiolase catalyzes both reactions. This one it catalyzes in the direction of breaking a 2-carbon piece off. In the case of ketone body synthesis, it moves in the direction of putting together a 2-carbon piece onto there. But suffice it to say that the result here is that we have an acetyl-CoA, and since we're in the mitochondrial matrix, where can we use acetyl-CoA? Citric acid cycle. So it's already sitting there, positioned in the right place now for the citric acid cycle to oxidize this guy to carbon dioxide. So what have we made? We've made 1 FADH2, we've made 1 NADH, and we've made a fatty acid shorter by 2 carbons. Now that might not seem like very much, but remember that this acetyl-CoA in the citric acid cycle is going to generate 3 more NADHs, 1 more FADH2, and 1 GTP. The energy stored in fatty acids is greater per carbon than it is for glucose. It's for this reason we use fat and fatty acids as our primary storage form of energy. Glucose is used primarily for quick energy because it can be readily dissolved in the aqueous environment of the blood, whereas fats and fatty acids have to be packaged up, and that takes longer to do that. Okay, moving right along there. I think I just said that. Yep. Okay. And there's the parallel that I've been describing to you for those reactions. On the left, we see fatty acid oxidation. On the right, we see the oxidation from succinate down to oxaloacetate. The reactions are virtually identical. Okay. Unsaturated fatty acids go through a little different path for oxidation. And that's because those double bonds that are out there actually get in the way. One of the things that you probably noted but didn't think about it because you were furiously writing notes as I'm up here babbling is that there's a trans intermediate formed in fatty acid oxidation. That trans intermediate is sometimes people confuse and say this is what trans fat is about. It's not. Okay? So the trans intermediate is a normal part of the oxidation of fatty acids. It's transiently formed. Transiently, get it? Haha. Transiently formed. It's a dead crowd. Maybe I'm just rambling too much today. I haven't told you guys any jokes this term, have I? Would you like a joke? Yes. Oh, God, yes. All right. You probably heard this if you've ever watched my videos. It's my favorite joke, but I'm going to tell this joke because I love this joke, okay? It concerns this hitman named Artie, okay? And Artie's this little guy that decides he wants to be a hitman, all right? And so he looks out in the world and says, you know, look how everything operates. You know, these high-tech companies get big by giving away stuff for free. And then once everybody's got all this stuff for free, then they start paying for it because now the company raises the prices and so forth. So he's pretty smart. He figures that he's going to start out real cheap. So he puts up signs all over the neighborhood and it says, "We'll kill people for cheap," okay? Right? And so he puts his phone number on there and everything, and he goes home and he just waits, and the phone rings, and he gets this call, and it says, "Are you Artie?" And he says, "Yes." And says, "You'll kill people for cheap?" And he says, "Yes." And he says, "Well, I want you to kill my wife." And he says, "Oh." He says, "Okay." And the guy says, "How much are you going to charge?" And he says, "I'll charge you $1." He says, "$1?" He says, "Well, I'm just starting out. Just start out cheap. You know, I'm going to do it for $1, right?" He says, "Great." Artie says, "How do you want me to kill her?" He says, "I get to specify that too?" And he says, "Yeah." And he says, "Well, why don't you strangle her?" Okay. So he says, "Okay." So Artie says, where's she at right now? And he says, "Well, she's down at the grocery store," describes what she looks like and everything. And so Artie goes down to the grocery store and he looks, and sure enough, there she is. And she's all by herself. And he goes up and he grabs her in the grocery store and he strangles her right there in the grocery store. His career as a hitman is already off to a great start. Oh, but one problem. Somebody saw him, right? Well, you can't have a witness if you're going to have a career as a hitman. So he goes and he grabs the witness and he strangles the witness right there in the grocery store. Now he's got, oh, damn it, there's another one. He goes over and he grabs the other person and he strangles them right there in the grocery store. And finally he looks around and he sees no witnesses. And he goes running out of the grocery store. And the police go running after him. And the police catch him. And the headline in the newspapers the next day says, "Artie chokes 3 for $1 at the grocery store." Oh. That is terrible. I love that joke. Yeah. Artie chokes 3 for $1 at the grocery store. It's going to be kind of hard to come back to this after that. I can see that. I hope I don't have to explain it to anybody. All right, if you'll bear with me through this, I'll go through it fairly quickly, and then I've got a cute song for the day. All right. So the beta oxidation that I've described to you works beautifully for saturated fatty acids. Unsaturated fatty acids have double bonds that actually pose problems. Now, I mentioned that trans fat, has nothing to do with trans fat. Trans fat actually happens because of chemical modification of food. When you see the words partially hydrogenated on the ingredients of anything, that's the chemical modification. Partial hydrogenation is done to fats to increase their saturation. And by increasing their saturation, you raise their melting point, and it appears in many cases to actually increase the longevity of food, the stability of the food as well. One of the things we've learned in more recent years is that hydrogenation causes the cis bonds, which are normally found in fatty acids, to form trans isomers. And those trans isomers have some very drastic health consequences. When we talk about increasing LDLs, trans fats will do that. Okay? Don't believe the labels that say this food has no trans fat unless the ingredients do not mention partially hydrogenated, because the food industry is able to say something has 0 amount as long as it has less than half of a gram per serving. That's a lot of trans fat. Okay? So read your labels, make sure that when you think you're getting something that's not trans fat, you're not getting trans fat. Well, that's off of the subject here. The subject here is about how do we oxidize fatty acids that are in fact unsaturated. Well, there are two enzymes that are critical for this. One is an enzyme called endocytosis isomerase. It's the easier of the two to understand. Let's look at this fatty acid that's got a double bond way here in the middle. Beta oxidation of this fatty acid starts out just like it does for a saturated fatty acid, and it cuts off 2 carbon pieces until we get close to that cis double bond. In this case, the cis double bond is shown at position 3 and 4. The cis double bond at position 3 and 4 is converted into a trans double bond at position 2 and 3 by this enzyme. Really simple. Move it the way I want it, and all of a sudden now I've got this guy, which the cell can oxidize, because this is just like the intermediate that's normally found in fatty acid oxidation. The cell goes through that oxidation, and it removes that. So that this 2 carbon piece, I don't show the steps, but this 2 carbon piece is removed. We look over here, we're now closer to this double bond, and the process of oxidation, the beta oxidation, has started because we've made something that has a trans double bond at positions 2 and 3. That's the first step in the process. We're starting that next round. However, the enzyme that would normally take and hydrate this doesn't do it. It won't do it. So this double bond has to be fixed. And it's fixed by this enzyme called 2,4-dienyl-CoA reductase, and yes, unfortunately, you need to know the name of that, and NADPH. Why do we need NADPH? Because it's a source of electrons. And why do we need a source of electrons? Because we're converting 2 double bonds into 1 double bond. So these 2 double bonds up here are converted into a 3,4 double bond. And the 3,4 is isomerized into a 2,3, and beta oxidation continues. Because of these 2 different enzymes, we can handle all of the normal fatty acids that are unsaturated that are found inside of cells. Okay? Okay. Well, that said, I promised a song. Let's do a song and move forward. This is a song called When Acids Get Oxidized.
Fatty acids carried
By CoA, are oxidized inside the mitochondriae. They get to there, as you have seen, by hitching rides on carnitine, and it goes away when acids get oxidized. Electrons move through membranes, yes, it's true, it's true. They jump from complex 1 onto CoQ. The action can be quite intense when building proton gradients, and it's good for you when acids get oxidized. The protons pass through complex 5, you see. They do this to make lots of ATP. The mechanisms you should know go through the stages LTO, so there's energy when acids get oxidized. Okay, see you guys on Wednesday.